very much. Okay, yeah, so I will talk about our experiments using visible satellite images in data assimilation. So these were experiments performed in the Hans Ertl Center for Weather Research in a collaboration between LMU Munich and the German Weather Service. And most of the plots I will show you are actually from Stefan Geis and Lido Bach. Okay, so here's an example for a visible satellite image. It's the bushfires in Australia a year ago. The image is taken by Himawari 8 in 3 visible channels with resolutions of 1 kilometer. I think one of the channels has even 500 meters. And we will get very similar images of Europe when Meteosat's 3rd generation will be started in the next years. So these are high-resolution cloud observations that are well suited for convective-scale data assimilation. And so far, mainly the infrared channels have been considered for data assimilation, mainly because a suitable forward operator was missing. And a few years ago, we implemented such a forward operator. It's called emphasis and is sufficiently fast and accurate. And now we can also use these images. And that's really nice because they contain additional and complementary information compared to the infrared channels. So we can see clouds in both in the visible and the infrared channels, but the signals depend differently on the cloud properties. And just to give you a bit more detail, here's an example. Here you can see the signals we see in a visible 0.6 micron channel and the infrared window channel at 10.8 micron for a water and the ice cloud. So we are just looking at single clouds and increasing the water or ice content of the clouds. And you can see here for the visible reflectance, you start to see something at 10 to the minus 2 kilograms per square meter. And then the signal goes up and saturates somewhere. And the signal for an ice cloud is very similar. It's just here we have larger particles. I've assumed 40 microns. And so for the same mass, the ice cloud is less effective in scattering in the radiation. So this is shifted to the right. In the infrared channel, so we see here brightness temperature. And you also start to see something at 10 to the minus 2 or somewhat below. And then the signal saturates at some point. And of course, for the infrared channel, the saturated signal is basically the cloud top temperature. So it's a higher temperature for the water cloud, which is located lower than the high ice cloud. So at first glance, it seems as if we would just get additional information in the infrared channel, that is the cloud top temperature. But actually, there is also information contained in the visible that we do not really see fully in the infrared channel. And that if you look at the range over which the signal varies, the range in the water content, you can see it's much larger in the visible. It's more than 2 orders of magnitude here marked by these horizontal bars. And in the infrared, this range is much smaller. And now if you superimpose these horizontal bars marking these ranges on the liquid water path distribution from a model run, here it's from some 30 days of ICAN D2 data, you can see we cover a much larger range of the model clouds in the visible than in the infrared. We have only limited information on the cloud thickness in the infrared, but on the other hand, we get the cloud top temperature. And in the visible, we have a much larger range. And actually, this is the range where most of the clouds are and where changes in the water path have a strong impact on solar radiation. So this means that visible images are useful for model evaluation to constrain the cloud water content. And we have just submitted a paper on this topic. But here I will talk on the second application. So assimilation of visible image should improve the cloud location and also the thickness, and it should improve the surface radiation. So before we come to the assimilation results, let me just quickly say a few words about the operator. So it's the main trick. Radiative transfer in visible is complicated by the fact that multiple scattering is important. And this makes standard methods really expensive. So we need hours to compute one synthetic image with standard methods. And therefore, we developed more emphasis. The main trick used here is to really simplify strongly the vertical structure. It turns out you can, if you take all the water cloud layers of a model column and replace them by one uniform water cloud, and do the same for the layers containing ice clouds, and then compute radiative transfer for this very simple situation you get, which is depicted here, you get almost the same reflectance. So details of the vertical cloud structure just do not really matter in the visible, which means we can describe the clouds in the model column by only 4 values, the optical depth and then effective particle radius for the ice cloud, and the same for the water cloud. And then we need just 3 angles to define the geometry and an albedo value, and then we have fully defined our problem using 8 parameters per column. And then, of course, we can compute an 8-dimensional lookup table where we really store pre-computed reflectances, computed with standard methods, and yeah, that can be done. And we did an additional step and used some form of lossy compression to compress this lookup table from 8 gigabytes to 20 megabytes. So this gives us a sufficiently fast and accurate method, and that has been implemented in RTTOF by DWT in collaboration with Met Office in the framework of the HumidSat Numerical Weather Prediction Satellite Application Facility. So this is publicly available. And I also want to mention we have now a prototype for a new version that is based on neural networks. And this seems to be really much more efficient. So now we need to compute only 8 megabytes instead of 8 gigabytes of training data. And also the memory requirement goes down by a factor of 1,000. And this will allow us to increase the accuracy and extend the capabilities of the operator, for example, including aerosols or going also to absorbing channels just by including more input parameters. Okay, so to come to the assimilation experiments, we have done some case studies before with Cosmo, but now we've done the first multi-week experiments using a near operational Icon D2 Kender setup. So the Icon model domain is the red rectangle here. It says the grid resolution is 2 kilometers. We use the local ensemble transform Kalman filter with 40 members and a deterministic member. The assimilation window is 1 hour. We start forecast every 6 hours, and we assimilate about 10,000 conventional observations per hour. So these are basically the pink and blue dots here. We use latent heat nudging, and the green rectangle here, these are the meteosat visible severity reflectances, which we have super up to 12 kilometers. We are assuming an observation error of 0.2. We do not use any vertical localization, but we use horizontal localization with a scale of 35 kilometers. We are doing also some quality control steps. So we discard observations where the sun was too low or where snow or aerosols affected the signal. And I will show you 2 types of experiments. The ones labeled with conv are using only conventional observations, and the ones labeled with visconv use additionally the visible observations. So it is about 15,000 observations per hour. I will show you results from 2 test periods, July 2019 and August 2020. And the main difference here is that the first experiment was without radar data assimilation. So we have latent heat nudging in this experiment, but we do not really assimilate radar data. In the second experiment, we assimilate reflectivity and radial velocity, which are again about 40,000 observations per hour. So let's first look at the first period and the 0.6 micron reflectance error in the assimilation cycle. So here I show you plots of the mean absolute error in reflectance as a function of the time of the day averaged over this July period. And the uppermost dashed line, that's actually 2 lines. That's the first guess and analysis error of the conv run. And you can see that the conventional observations they do not really lead to an error reduction in the cloud distribution. However, if we assimilate the visible images, we can reduce the analysis error by 50%. And if we then do the first guess forecast for 1 hour, you still have an error that is 25% lower than in the conv experiments. So we're really reducing strongly the cloud error. We also see some improvements in the bias. So the bias is smaller for the for the visconv experiment, and it's also reduced in every assimilation step. And it seems we have a bit too many clouds in the morning and too few later. So now it's interesting to ask, how are we reducing the reflectance error? Is it by creating and destroying clouds, which includes moving clouds, so correcting displacement errors? Or do we also improve the error by adjusting the thickness of the clouds? So to look into that, we make a simple assumption that reflectance greater than 0.25 means cloudy, and smaller means clear sky. That's of course a bit approximate, but at least over land it should be not too bad as an assumption. And then we can sort our observations in 4 categories. So they are explained here. So in this on the lower left, the plot that gives you on the horizontal axis we have the first guess reflectance, and on the vertical axis we have the analysis reflectance, and then we can sort here all our observations into this diagram. And in category C we have observations that are clear sky in the first guess and stay clear sky in the analysis. Then we have cases where we have a cloud in the first guess, which is clear sky afterwards. So we remove a cloud. That's this region is R here. And then we have cases where a cloud is generated. And the region A is where the cloud is either not modified at all or its thickness is adjusted. And to the right, you can see how often these 4 cases occur in the visconv experiment. And you can see most of the observations are in A and C, and only in less than 5% we remove or generate clouds. But now if we can look into how these 4 categories contribute to the mean absolute error in reflectance. So this is information is provided here. So for every time we have 2 bars, the left bar is for the first guess and the right for the analysis. And sections of the bar are colored according to from which category they are coming. And you can see now the categories R and G are really dominating. So they are dominating the error, and they are also dominating the error reduction. So when you go from first guess to analysis, it's mostly this orange and green bars that are shrinking. So here the main part of the error reduction occurs. But you can also see these blue bars from category R are reduced in the analysis. So we have both. So the error is mainly reduced by creating and destroying clouds, but it's also improved by adjusting the water and ice content. So that's nice. That means we are really using that information from the observations about the thickness of the clouds. So this is just an example, so an illustration how this works. This is an observation, the deterministic first guess model equivalent from the visconv experiment, here from the conv experiment. And in this case, you can, for example, see that in the blue ellipse, the brightness of the cloud matches much better in the visconv experiment. It's too low in the conv experiment. So here the thickness of the cloud was corrected, and in the orange circle there are no clouds in the observation. There are a lot of false alarm clouds in the conv experiments, and they are strongly reduced in the visconv experiments. Okay, so what about the forecasts? So here I show you the fraction skill score for reflectance with larger than 0.5. So this means at least clouds of medium thickness. And on a scale of 24 kilometers for the deterministic member, and for this 4 different times of the day where we started the forecast. And you can see at 6 UTC and 12 UTC we have nicely increased the score, and this persists for more than 6 hours here. And even for the forecast started in the evening, sorry, we still see some improvement after the night. So of course, during the night, we cannot verify with visible reflectances. So let's look at the surface irradiance. So to be more precise, the global horizontal irradiance. And the plots, the quantity plotted here is the reduction of the GHI root mean squared error in percent. So for example, we see here a bar of 25%, which means by additionally assimilating the visible images, we are reducing the radiation error initially by 25% in this case. So this is really a huge improvement. And after 6 hours, we have still 5% left. And here again, still after the night, we see a bit of influence from this assimilation. And yeah, we get similar results for the 12 UTC forecast. We get a little bit less impact at 18 UTC, which could be related to the fact that here 3D radiative transfer effects are more important as the sun is lower. Yeah, but we still get an improvement of the radiation also after the night. Okay, so now how does this change when we include also radar data assimilation? I'm sorry, I have not really exactly the same, the plot in the same style here, but I have adjusted the scales a bit. And well, you cannot really directly compare this July and 2019 and August 2020 periods because they're really different periods. And also we have used different model versions. But the important point is also in this experiment where we have radar included, we see a big improvement in the radiation. So it's not that when we include radar that all this improvement is gone. And basically that's what you expect because the radar can see only the convective clouds, but in the visible we see also non-convective clouds and correct errors. Okay, and finally, precipitation. It's also, we see a small but consistent improvement due to the assimilation of visible reflectances. Here to the left, it's the fraction skill score for very light precipitation on the 22 kilometer scale, and to the right for more intense precipitation. And yeah, it's not very much, but it's consistent. And finally, what about other observations? Here you can see the improvement for surface observations. We see a neutral impact on the pressure, but we have improvements on the humidity at 2 meters and the temperature. We see this also in the radio sound verification. There are slight improvements here, and we have more neutral impact in the wind speeds. So to conclude, visible images contain information on cloud locations and water content, and we can use this information in simulation experiments, where we see improved cloud location and thickness, and also we improve surface radiation temperature and humidity, and have neutral to slightly positive impact in other variables. And the next steps will be to do experiments for other weather situations, example for fog, assess the impact of different improvements to the forward operator, also improve the assimilation by using an error model and improving quality control and bias correction. And then we will also use other channels like near infrared channels. Okay, thank you.
Thank you very much, Leonhard, for this nice presentation. Really promising results. And yeah, we're looking forward to what is coming up next. So we have 2 questions in the Etherpad so far. The first one by Florian Meyer. He asked, are hydrometeors part of your control variable?
Well, I'm not sure about the radar experiment. I think in the first experiment they were not.
Okay, so you do not update the hydrometeors when assimilating the BIS?
No, I don't think so.
Okay, thank you. The second question by Takumi Honda from Riken. Are there observation error correlations between visible and infrared channels? But I think you only assimilated visible in this case.
Yeah, we didn't look into that, but well, there may be some, yeah.
Okay, yeah, that's something to come in the future when you also include the near infrared channel. Then there's another question coming. I'm just waiting to be written. Okay, Lilo Bach is just answering yes. Cloud water is part of the control vector.
Yeah, so, cloud water, but not rain and.
Yeah, not rain. Yeah. Okay, so then there are no more questions. If there are more questions, simply write them into the Etherpad. And now we are coming to the final two talks. And